the calc-related material that I want to do today also includes the general concept of operational semantics, which is an approach to defining the meanings of programs in explicit programming languages that have syntax. In my last lecture, I showed some examples of reasoning about state machines where we built a special purpose relation to explain the behavior of a single program. And in general, we'd like to be able to explain the meanings of whole classes of programs in particular types of syntax. And this approach, operational semantics, forms the foundation for most modern reasoning about programs, including what Amal will be talking about in her lectures on logical relations. So to set the stage for that, I need to show a generalization of a relation that we defined last time. This is the general idea of the transitive reflexive closure of a relation. And I've written it over here in standard inference rule notation. So if we have any relation, it's a binary relation over some arbitrary set A, and I'm writing the relation as a right arrow symbol to express the intuition of stepping from one state to another. We define the transitive reflexive closure by two rules, and there are actually many different sets of rules that define the same relation. This version happens to be the most convenient for the proofs that I'm doing. First, it's a reflexive relation, so any element is related to itself by the closure of this arrow. And also, if we can take one step in the original relation, and then from there take 0 or more steps to some final state, then we can compose together these two kinds of steps and get one big step here. So transitive reflexive closure stands for taking 0 or more steps of some underlying relation. We'll apply this to notions of taking a step in the execution of a program. And it also has many other applications in math and computer science. So on screen here, I have the code for formalizing this in calc. I should ask first, in my first lecture, someone suggested a dark background might be more readable. What do people think? Is there any consensus about white or dark background? Yeah?
I don't know about the background, but one thing a few people said might be good, especially once you start doing some proofs, is sacrificing font size for the ability to see the a few more lines at once.
Uh-huh. Okay, I'm going to put it back to the normal font size then. You can tell me if this is too small. Okay, then I'll keep the white background unless there's an undercurrent of dissent that no one is revealing now that I'll learn about later. All right, so are we happy with this size? A little bigger? So let's see, I went to 200 last time, and so I'll do probably like 160 or something. Is this good? Yeah. Okay. All right, so here's the calc statement of the definition of transitive reflexive closure. It's written to be parameterized over a type capital A and a relation capital R over capital A. You know it's a relation because it's a function that returns prop. And star itself is then a relation of the same type. And by the way, this argument capital A is going to be inferred everywhere that it appears because we can compute it from the types of the other arguments, so there's no need to write it. And I'm using the same distinction between parameters and other arguments that we saw in AGDA, where some of the arguments to the type family appear to the right of the main colon here, and others appear to the left, some appear to the right. And the ones to the left stay the same across the recursion in the type definition. The ones to the right can change throughout the recursion in the type definition. So x steps to x. If x1 goes to x2 and x2 goes to x3 with 0 or more steps, then x1 goes to x3 with 0 or more steps. That's what this says. Yeah?
Is A implicit because you didn't give it a type?
It's implicit because it's possible to infer, given the types of the others. For now, just assume calc always makes the right choice there. It's because I set this option set implicit arguments that deduces good choices of implicitness. And so I said this is the transitive reflexive closure, but it's not immediately obvious that this is a transitive relation. Luckily, we can prove that easily enough by induction on, if we have two star steps, we can do induction on the proof of the first one, and we can pretty easily establish that it's a transitive relation. I won't even step through the proof here. You can step through these 6 lines or so on your own if you'd like. All right, so that's the foundation for being able to start talk about the semantics of the lambda calculus. And I'll present 3 different ways of defining what it means to run a program in the lambda calculus. And they're all useful for different reasons and different contexts, and we'll relate them to each other, so in some sense you always get to pick the best one for the job. So here's the regular old lambda calculus, which we've seen before in a few different forms. There are all sorts of different programs we can write in even a language as limited as this one. So let me write out a few examples, and we'll use these to see how the different approaches to evaluation work. So the shortest closed program that we can write, closed means it contains no variables that are not mentioning binders within the term itself. The shortest closed term we can write is the identity function. So this is a function that when you call it on any argument, it returns that argument. And of course, we can apply the identity function to itself. What should the result be of evaluating this expression? Yeah, we should get back to the first line again. And we can continue this highly productive exercise of continuously duplicating terms as many times as we like. We can write all sorts of different identity functions. When we evaluate this term, intuitively we expect it should eventually get back to the first line. And so we want to write down a formal relation that captures what we mean when we talk about evaluation here. So the first of the 3 approaches that I'll present, by the way, here's the same substitution function I showed before. It's the idea of capture avoiding substitution we've seen in a number of contexts, including in the first week of lectures about proof theory and type theory and so on. Just take my word for it. This is an appropriate definition of substitution. Here are the 3 terms I wrote there in calc notation with some shorthands to make them easier to type. Here's the identity function. It's an abstraction over the variable x, and the body of the function is just variable x. We can also apply that to itself. Then we can apply the next thing to itself. And so we get up to identity 4 here, which is the third of those lines. These terms are all somehow equivalent up to evaluation. We'd like to be able to prove that. And to do that, we'll have to define what is evaluation. The first approach is so-called big step semantics. So let me write out the 2 rules of this judgment in the more traditional notation. I should say that in this lecture, I'm going to be sticking to what's called call-by-value semantics. There are a number of different ways you can handle parameter passing in a language like lambda calculus. And call-by-value is the version that appears in, for instance, the ML family like OCaml, and is also basically what's built into more mainstream languages like Java. And it basically means evaluate your argument to a function before passing it to the function. There are alternatives which you see in languages like Haskell, also associated with descriptions like a lazy language that would follow a different approach, but I will ignore those for the purposes of this lecture. So the first rule, which is a really simple one of this big step semantics, we're defining a binary relation which I'm writing as a double down arrow, which means the program on the left terminates and results in the value on the right, or the final answer on the right. And this just says a lambda abstraction is its own final answer. It needs no further execution. And things get a little more interesting when we go to the second of the 2 rules. It's kind of interesting that this is effectively, maybe there's some technical reason I shouldn't quite say it's a Turing-complete language, but it's very close, and we can write 2 of these rules that completely determine the execution behavior that makes it Turing-complete, or maybe just, morally speaking, Turing-complete. So I'll explain this after I've finished writing the different premises. Okay, so this is a rule for, in general, how you execute a function application. First, evaluate the expression in the function position, and it had better finish up as some sort of lambda abstraction. If not, then we're stuck. Of course, in this language, we'll be able to prove that if a program terminates at all, it always finishes with a lambda abstraction, but that won't be true for other languages with additional features. Then we evaluate the argument to some value. Finally, we plug in that value inside the body, E1 prime, of this function that was returned in the first case. And then we further need to evaluate that expression. And whatever is the result of evaluating the body with the right substitution, that is the result of the overall application. So this is sort of the essence of a very strong notion of computation in two rules. Yeah?
Is that first part of the premise basically just saying that E1 is a lambda abstraction?
No, E1 could require further evaluation to get to be a lambda abstraction. For instance, it could be that identity applied to itself over there. Okay, so this is an unambiguous idea of what it means to evaluate a program. One other thing I should define, how do we know what is a legal answer for evaluation? We can define a very simple relation in this case that I'll just call value. And the only values are the lambda abstraction. So we would like to be able to show that whenever big step gives us an answer, it really is a value. So we can check that Calc likes this definition. So far, so good. At this point, I guess I'll just ask you to take my word for it. This corresponds to what I've written over there, and it can be digested separately. We can sort of test this to check that it shows us that that big long term over there runs in this relation to the original identity function at the top line over there. And it's a kind of boring proof. Maybe I won't talk about through the details here, but we can just keep saying e-constructor, which means pick one of the two constructors of the big step relation, whichever one applies to the form of the goal, and use it. And feel free to introduce these question mark variables for arguments that we don't know about. For instance, every time we apply the application rule, we know that the first sub-expression needs to evaluate to some lambda, but we don't know which lambda. So we introduce question mark variables for the bound variable and the body of that lambda. So we don't really have to think too hard here. We just keep hitting this with the different constructors. In every case, by looking at the first argument to big step, it is completely clear which of the two rules has any hope of applying. We always pick the one that applies. Occasionally, we want to simplify to use the definition of substitution, and we keep going through that, and eventually we establish the theorem, which is that the long version of the identity function steps in, looks like about 10 steps, to the short version of the identity function. All right, so then here's the value relation that I wrote over there as the last rule. It just says a value is exactly any lambda abstraction. There's actually the formal definition of a value requires that this is a closed expression where the expression e doesn't mention freely any other variables besides x. I'm going to leave out that constraint here. We can still prove enough interesting things without worrying about it. But it is helpful to show that whenever any expression steps to some result, that result really is a value. So just as a kind of sanity check on this definition, let's try to establish that fact. Any suggestions on a good way to prove this? Yeah, let's do induction on the proof of the big step relation. So because we had two rules in the definition of big step, we should have two cases in this inductive proof. And here they are. The first one of them is that, so this corresponds to rule number one, which says an abstraction runs to itself. So we have to show this abstraction as a value. How can we do that? Yeah, we can use constructor because this follows directly from the rule written at the bottom there. In the second case, we have all these hypotheses, but this is actually a simpler goal than it looks like at first. How do we prove this? We can run assumption because we had these three premises here, and the final answer is copied out of the final premise that goes down from this premise to this answer, and we have an induction hypothesis for every premise telling us the answer it returns is a value. So the third induction hypothesis directly gives us the property that we're looking for here. If we had used case analysis instead of induction, if we'd used destruct instead, then this would not actually have been, we would have gotten stuck in the proof. We need that induction hypothesis. All right, any questions about big step semantics before I go to the next kind? All right, so the next kind, you might even be able to guess from first principles and properties of the English language that if we did big step, we're probably going to do small step or medium step or something. It turns out it's small step. And small step semantics is a different style which is applicable in more cases somehow. For instance, if you have a program that doesn't terminate, then big step semantics doesn't tell you anything about it. You can't derive any fact about it. Whereas with small step semantics, you'll still be able to conclude things about the program. And small step semantics is also often convenient for reasoning about concurrency or non-determinism or other relatively more advanced kind of features in a language. And there are going to be 3 rules in the first version of this. And I'll also implicitly, for all these semantics, I'll stick with the call-by-value style where we evaluate a function argument fully before calling the function. Oops. So the first rule here is kind of the most fundamental one. It tells us what to do when we are ready to actually call a function. So we have some lambda abstraction applied to a value. The way we run this is we substitute in the body of the lambda abstraction in the usual way. And this rule only works when this argument v is a value. Another rule says, here's how to make some progress evaluating an application expression. It says if you're able to step the first of the subterms in an application, then you can sort of port that step to work inside the larger context of the application. You can take a step on the left-hand side of the application and you can perform it, leaving alone whatever appears on the right-hand side. And there's one symmetrical rule to that one that completes the definition, which says, you might be able to guess how this works. This one lets us take a step on the right-hand side of an application. Under the condition that the left-hand side is already a value. So these extra premises about certain things being values are important to define exactly what we mean by call-by-value execution. There's a nice property that this relation has. It's sort of a general property we might talk about in semantics or relations, where that property would no longer be present if we remove those extra requirements for things to be values. Any ideas what I might be thinking of? Yeah? Sure. So that there's a standard adjective to apply to a relation or to a semantics that works here that wouldn't work if we removed those value premises. Yeah. Yeah, this is a deterministic relation. For any term that could appear on the left-hand side of this arrow, there's at most one term that could appear on the right-hand side. And at least if it's, I think this is true, if the left-hand side is not a value, then there's always exactly one. And if the left-hand side is a value, then there's nowhere it can step. And so the way that works is, for instance, if I left out this value requirement, that if I had an application, say this example term right here, then we could choose whether to do a step of execution on the left side or the right side. Both of these sides are ready to have a so-called beta reduction using the first of the rules over there. But this rule disambiguates and tells us we couldn't possibly apply this rule first because it requires that this first sub-expression is already a value, and over there we don't have a value, we have a function application. So this forces us to evaluate the function position first, then the argument position, and then when both are done, we can apply this rule that actually substitutes inside the body of the lambda expression that we came up with. And here is the calc code for defining this relation. It's just read off from that notation in the usual way. And we can repeat the example derivation from the big, long, redundant identity function here to show that it gets to the simple identity function. But we're not just going to say identity for steps to identity. It will take multiple steps, and we do that using this transitive reflexive closure operator that I introduced at the start, which I called star. So we can apply the star relation where the underlying relation is small step, and this will show us that identity for gets to identity. And it's a pretty similar proof where we just keep applying different constructors. I won't go through the details here. In one case, I had to give the constructor because the constructor guessed it must be the first application case, but actually it's the second one. Otherwise, it's just running constructor steps over and over again, picking the right ones in general, simplifying the definition of substitution where possible. So we get to the same answer this way. All right, any questions about small step semantics before we start proving some theorems about it? Okay. So one of the things we'd like to be able to prove is that small step and big step semantics are equivalent in an appropriate sense. And we can't just say that each relation is contained in the other, because that doesn't work. Small step might take just one step and not finish an evaluation process, while big step always goes from start to finish in the execution of a program. So one natural way to phrase this connection has to do with what happens when we run small step 0 or more times and we finish at a value. That should be equivalent to running big step. And so these two theorems give the two directions of that inclusion. One direction says if we run small step 0 or more times to get from e to v, and e is a value, then we can also take a big step from e to v. And the other direction says whenever we take a big step, we can mimic that by taking 0 or more small steps. So let's try to prove each one of these directions. Any suggestions for how we can prove this one? We know that we can take 0 or more steps in the small world to get to a value, and we'd like to mimic that with one big step. Induction 1 is always a safe bet to try first, so let's go for that. Let's run induction 1, and probably in this case, I'll run simple intros just to be safe and simplify some things. Okay, so now we know, so because the star relation, which I showed at first, has two rules, the reflexivity rule and the quasi-transitivity rule. We also proved transitivity as a lemma. We have two cases in this inductive proof. One is the case for reflexivity, so naturally we need to show that some value steps to itself. We know it's a value because there's a premise for it. So any suggestions for what is a good step to take here? Wow, so many ideas. I hear e-auto and constructor, and I don't think either one of those is going to do this, but we can verify. Constructor has no idea what to do. Big step requires, like I said, erased big step, but the left-hand side always needs to be either a lambda abstraction or an application, and this isn't either. Okay, let me get to the other suggestion first. Someone suggested e-auto, which I think I may not even have presented yet, which doesn't do this either. And I'll explain what that is in a moment. So, okay, so I heard a suggestion to run inversion h. What that basically means is we know that x is a value. The fact that it's a value must have been derived by the one rule I presented earlier for values, which says a lambda abstraction is a value. So if we run inversion on h, then we'll get one case for every rule of the judgment value that applies here. In this case, there's just one rule, and it could have been used. So now we know that x, in fact, equals some lambda abstraction, and that abstraction has conveniently been substituted down below in our obligation about the big step semantics. So now a constructor works because we had a rule telling us literally any lambda abstraction steps to itself. So far so good there. All right, so here's the more challenging second case, which says, let me sort of read it in English. We took one small step from x1 to x2. Then we took 0 or more steps from x2 to x3, and we're done because x3 is a value. By the way, if this true fact holds, then it's also true we know how to take a big step from x2 to x3. So any ideas how we could make progress here?
First, do a definition to combine H1 and RH.
Okay, so we could do some relatively shallow stuff and get rid of this extra premise, which we know was easy to satisfy. And now here's how things look. That's intuition applies the rules of propositional logic to simplify the goal. Any other ideas? Sorry? Destruct x1. We could also just do inversion on h, and then that might help us. Let's see what happens. Sometimes it's simple to, after inversion, run a tactic called subst, which is going to take all these, watch, so here we got these equalities that said some variable equals something. If I run subst, then we'll get rid of those variables and just replace them everywhere by the things they're equated to. So the goal gets a little shorter. So I'll chain these together, so those happen at once. So now we learned, let's see, here's our original fact. We learned that we must have applied, we got 3 cases because there are 3 rules for the small step semantics written over there. And we have that we applied the beta reduction rule, where we applied a lambda abstraction to some value, and that takes a step by substituting in the body of the lambda abstraction. Does this help us? What do we know what to do here? Yeah?
Inversion on H1.
Let's see. Okay, so this will tell us that x3 is actually a lambda abstraction. It's often helpful to follow the chain of execution here. We somehow got from here to here, we got from here to here, and now we're trying to get from here to here. So here's let's call this A and this B. Here we have A goes to C, C goes to B, and we have to somehow compose those together to get this answer. And try inversion on H2 as well. This is going to be trickier because this rule could apply, it could be either of the 2 rules. This substitution operation might give us either of the 2 cases. It might be a lambda or it might be an application. And subst didn't even help us here. We have to somehow figure out what E1 would have led to this abstraction being the result of substituting for x. At this point, we can keep picking things to invert, but I think this probably isn't the best strategy. We can sort of rethink this at a higher level and make this proof go better. Any ideas?
We can go back to all the inversion and add a lemma.
Adding a lemma, I like that idea. Any ideas what kind of lemma we want? Let me back up before we did the inversion. Or no, that one was good. This case, this case. What would be a good lemma to use here? If we had whatever lemma we liked that was somehow just the right level of generality, not too specific, what would we expect to use here? Yeah?
If you small step from A to B and then step star from B to C, you can compose that as a star step from A to B.
That's actually one of the constructors of star.
Oh.
We don't have to worry about that.
Well, then can we compose H and H0?
H and H0 already came about from induction on a star fact like this. So we could compose them and get back where we started, but it wouldn't help us directly here. That's really close to the right lemma.
Small step star with big step.
Exactly. So we can basically take the rule for star small step, replace the place where we say star small step with big step, and that will be what we need here. Let me make this a little more concrete. I'm actually going to apply a common technique of copying this and turning it into a lemma statement and generalizing as appropriate. I'll make some more space here. So this is a lemma about taking first one small step and then a big step and composing them. And I'm leaving a marker here where I'll fill in the variables that we need later as we realize we need them. So let's say we stepped from E1 to E2, and then we took a big step from E2 to E3. And it better be the case that we can now take a big step from E1 to E3. So what this is basically saying is if you have a big step, you can add an extra small step onto the beginning of it, and it remains as a valid big step given your new starting point, which needs more reduction than your original starting point needed. Okay. So, any suggestions how we prove this? Induction 2. Let's see what happens there. Get that again. So here we know that some term took a small step to a lambda abstraction. We want to know it takes a big step to the same lambda abstraction. How do we feel about that? We could do that, but I think actually we'll do more work this way than necessary. And actually, there were sort of two plausible choices how to start this proof, and I like the other one better. Let's do induction on the small step derivation. It'll just come together better, I think. So we'll get 3 cases, one for each of those 3 rules. And I'll put in intros afterwards. So here we have that we have the application of an abstraction to a value, and it should get somewhere. And up here, we happen to know, conveniently, that the substitution we would need to apply to do that gets to the place we're trying to get to. So this is promising. What might we want to apply here? Remember, Big Step had 2 rules, one for each kind of expression, either an abstraction or an application. Yeah, we can apply constructor here, and I think it'll actually be e-constructor because we don't know immediately what are all the values the intermediate terms evaluate to. So we'll figure those out in the course of doing this. But we know we should apply the application rule of Big Step. We have to first figure out what does this abstraction step to? Good question. Constructor will figure this out. Of course, an abstraction steps to itself, and by applying that, we learn this question mark variable equals this guy, and this question mark variable equals this guy. So, for instance, we'll see, since question mark x appears here, after I run this, we'll see it replaced with just regular x, and question mark e1 prime will be replaced with e1 down here. So now these used to have question marks. Now they've been determined, so the question marks are gone. We need to show what v steps to. And actually, we're kind of stuck here. We're not going to be able to do this directly because we don't know. The Big Step rule applies only when v is a lambda abstraction. And if I use inversion here on h to reveal what lambda abstraction it is, the problem we get is that we need to get that this abstraction steps to something. And this variable, this question mark variable, was created in a context where the variables x0 and e didn't exist yet. So we're not allowed to mention them in here. And this expression is kind of telling us that it's recording that basically this variable was created before this operation, or something like that. Yeah, so let's just move this inversion earlier so that we have those variables already when we do the e-constructor. And now we'll be ready to mention all the things we need to mention. So the first case is the same. The second case, now we can do constructor here as well.
So it wouldn't have worked if you had not moved it up?
Yeah, we would have gotten something quasi-nasty. Oh no, maybe I don't know what I'm talking about. Or maybe actually this is telling us, so maybe it does work fine. Coq may have recorded a substitution that makes this work out nicely, and this is a relatively new addition. Let's see what's happening here. V2 should appear here. It says V. Yeah, so it remembered that V, it remembered the equation and somehow substituted things out so it was fine. Okay, so that was a false alarm. Sorry about that. And now we can use our assumption. All right, so far so good. So now we're in the case where we took a step on the left-hand side of the application here, and we are lifting that up to the full term.
One stupid question.
Sure.
What's the difference between focus rules, focus subrules, and the simple subrules? It seems that here there were 4 focus subrules.
I don't know. I ignore those words on the screen. Sorry, I can't have a better answer for that. I would think you have to focus on one thing at once. That's what I'm used to, so I don't know about this 4 focus subgoals. This is a relatively new addition to the chatter that Coq produces. All right, so we have here that this application steps to our final answer. We have to show this one does. And the difference is E1 prime is where we get from E1 with one small step of execution. So what could we do here to make some progress? The hint is that Big Step has exactly one rule for every constructor that could be used in its first argument. So we can do inversion on this big step fact. We know that the thing on the left of the big step is an application, so we can tell exactly how this must have been derived. So I will do that inversion. Now we have 3 big steps that we know about. And so that's a good start. And these look a lot like the premises we would need to apply the application rule to our conclusion down here. So let's optimistically try to apply that rule. The first thing we need is that E1 steps to some abstraction. And what we have is that E1 takes a small step to E1 prime, which then takes a big step to this thing. This is looking a little suspicious. I think I haven't quite stated the lemma right. So this illustrates a common pitfall in the stating lemmas and doing induction, I think. There's a better way of doing that. I think I won't explain what that particular command means. But what I'm going to do is I'm going to move one for all quantifier later in the goal. And why is this a good idea? The reason is that all the variables that are for all quantified before the thing we do induction on remain fixed for the entire duration of the induction. By moving one of the quantifiers later, it remains as a quantifier in the induction hypothesis, and we're allowed to pick different values for it at different points in the proof. And where the point where we just were is precisely a place where the original value was inappropriate for the place we wanted to use it. We needed to make a different choice. So now we'll see that in action, yeah.
In general, do you want to move for all as far forward as you can, or is it something not to do that?
If you know they don't change during the whole proof, you'll get simpler looking hypotheses if you keep them as early as possible. So it's sort of like you want to move them as early as possible so that your proof still works.
Okay.
At least that's my personal preference. It might not be universally shared. But then the first case here should keep working. And then now we should have a little bit better luck here. If I apply eConstructor, we're trying to show E1 steps to this abstraction. We know that E1 steps to E1 prime, and E1 prime steps to this abstraction. So it looks like we can, let's try applying our induction hypothesis here, which happens to match the form of our conclusion. Now that E3 is a quantified variable and it's not literally the same E3 we started with, it can match whatever we need, including this. And now we just need to show that E1 prime steps to some abstraction, and conveniently enough, here's our assumption, which tells us exactly that. So E assumption, we'll do this one. The E means deduce the values of the question marks in the process of finding a matching assumption. Now we need to know E2 steps to something, similarly available in our assumptions, and we need to know that this substitution goes to the right place, and here that matches an assumption even without using question mark variables. All right, so this last case should be very symmetrical with the case we just looked at. In fact, let's be optimistic and assume we're doing mostly the same thing. I might have to change some of the numbers on the hypotheses. We actually wanted to do inversion on a big step thing, which now has a higher number because there's an extra value hypothesis here. So let's do that. Apply a constructor. This time we would expect to use the induction hypothesis in the second premise instead of the first, because we're making a step happen in the second subterm instead of the first. So let me say this is probably an E assumption for the first premise. Then let's apply the induction hypothesis using the assumption, and then use an assumption like before. All right, so just make a little space here. That is our theorem. Whenever you can take a small step, if you can take a big step from the place you wind up, you can compose it and take a big step from the place you started. Any questions about that? Okay, yes.
At some point in the list, there were terms of the form variable quote 0.
Variable quote. No, I think that was an apostrophe, which we read as prime. It's just part of an identifier. Okay.
Prime, but what is the 0 after?
Just part of the identifier.
Just another identifier. So it's just another identifier.
Yeah. All right, so let's use this to finish the proof. It should be pretty quick. So we got to this point. We did a bunch of stuff, which we won't need. Let's apply exactly the small step, big step, compose. We might need to figure out some of the arguments on the fly. We need a small step from x1. More space would be good. And we happen to have exactly that. So E assumption gets that. We need a big step from x2 to x3. We can apply the inductive hypothesis and then use an assumption. And we're good. So that proves one direction of inclusion between these notions of semantics. So the next thing I want to do is make these into one-line proofs without, three-line proofs approximately, I guess, so that we don't have to think about all these details anymore. Are there any questions about the detailed version before I do that? All right, so let's see what we need to make this automated. I'll get to exactly what I'm suggesting. So the first thing we can do, let me show you something here. I'm going to use a command called hint constructors, where we pass it a list of relations, and I'm just going to list all the relations we've defined. Why not? And then every time we ask Calc to do an automated proof search, it's going to attempt to use every one of the constructors of each of these relations. And we'll say, search the space of all proofs up to some tree depth where the tree nodes can be any of the rules that are used to define these relations. This is a really powerful feature that can save you a lot of time working out details by just trying all the possibilities. You can tweak what depth of trees is considered to trade off between performance and generality, which theorems can actually be proved automatically. So let me show you this in action. What won't happen automatically in that kind of proof search is inversion. So I'll do it in the inversion that we found was important here. We want to do inversion on H in subst. And then I can run eauto, and let's see what it did for us. It did exactly what we did here. It figured out, it's somehow not so surprising that constructor assumption is an easy thing to figure out by brute force enumeration. And that's what eauto did. So we can delete all these in favor of just running eauto. And similarly down here, we did one inversion, and then eauto destroys it. And there's a lot of repetitiveness here. The same thing works here. So if we want to really automate this, we should make those inversions happen automatically too. And there's a simple way to do that. We can write this code, which is using a construct I sort of showed before, where we're going to do pattern matching on the form of the goal that we're faced with. Let's find any hypothesis. Doesn't matter what its name is. We're going to assign the name H to it once we find it. Anything proving value, we actually want to get rid of using the definition of value. So that automatically found the right hypothesis. I happen to choose the same name for this binder as the local name, but that wasn't required. And then eauto gets rid of it. So what I'm going to do is I'm going to write a little tactic here. We can write reusable units of proof automation functionality. I'll just pick a short name for it. And I'll say it starts out with intros, just like we did below. And then it does this as many times as necessary. It'll probably just be 0 or 1. Yes?
I think you need to clear H1, you getting infinite loop.
That's probably true. Good point. I'm going to clear H so we don't get an infinite loop. I guess alternatively I could write try instead of repeat, which does 0 or 1 times, and then we wouldn't have the same problem. That's a good idea. Thanks for that. And then I'll run eauto afterwards. So what this says is introduce all the hypotheses, find all the opportunities you can for using inversion on a value hypothesis, and then use eauto to search all proof trees up to a certain depth built using the ingredients mostly that are listed here.
Could you repeat about clear?
It just removes that hypothesis that's named. It disappears from the goal. So you can't use it anymore. And in particular, this tactic won't see it and get stuck in an infinite loop by repeatedly inverting the same one. Yes?
I saw that you cleared an inversion statement with the eauto, so could you just do eauto? So I'm assuming then inversion is also carried out by the eauto.
The result of inversion only went away when we ran eauto because eauto proved the whole goal. In general, that might not be the case. Eauto might not be enough to prove the goal, so it's sort of conservative to use clear directly to get rid of that hypothesis.
So there was an inversion step that followed the initial inversion.
Down here, there was always one inversion per proof case. There were 3 cases, 3 inversions.
I think there was one after the first chunk, there was an inversion H.
I'm pretty sure there wasn't, but we can, I don't know. If seeing whether this tactic works answers your question, then we might have an answer in 5 seconds. So I keep the induction and run T. Oh, it's not quite doing what I thought it was going to do. Let's see where it got stuck. It got 2 cases. Let's see. Oh, this was inversion on a big step, not on a value, so we need to go back and expand this a bit. I'm going to write, if you find a big step from, well, I could write this. Anytime you see a big step, do inversion on it and clear it and so forth. Any guesses on how well this is going to turn out? Yes, we get an infinite loop. And any theories about why that would happen? If the thing we're stepping from is a variable, then this inversion will give us 2 cases where all of the arguments to the subderivations of big step also have variables, and we'll keep inverting on those forever, and we'll just explore this tree of all the possible lambda terms, not very usefully, and we'll be in an infinite loop of inverting forever. So one thing we can do is check, do we have big step on an application? There will be only one rule that applies here, so this is always a useful thing to do. So let's try this. And now it's proved. And to finish up this proof, one thing we can do, we can record this fact as a new one of the primitive building blocks that proof search should consider. So every time we're enumerating all proof trees, please consider this as one of the nodes that should be included in the proof trees.
What is the resolve keyword for this?
It's resolve in the sense of resolution theorem proving from the history of languages like Prolog. Basically just means use it. Okay. And then it gets this one too with that hint. So in the hands-on exercise that I'll suggest, you'll be adding new features to the programming languages, and this proof will mostly keep working because it's so generic. You won't have to do any new work to handle new language features if everything works out well. Yeah?
What is the scope of hints?
Scope of hints by default are everything after them and any modules that import the module you're working on. You can use explicit local scoping if you want to, but that is, get ready for a pun, beyond the scope of this lecture. Yes?
And this translate molecules to big step and small step semantics in terms of equality, actual word system?
I don't know. How would you write that? We definitely can't write big step equals small step because they're doing very different things. It's not a direct equivalence.
Because it took implications of both sides.
It's not a direct implication between the two relations. There's this extra step of using transitive reflexive closure, asserting something's a value. So they're close. It's sort of morally close to being able to write equals, but there's an important gap between them. Yeah?
So a lot of the times when we do small step, we use evaluation context.
I'm going to get there.
Okay.
Yeah, that's the next commented section. Any more questions about this direction before we tackle the other one? All right, so let's prove that other direction. Whenever you have a big step, you can simulate it with 0 or more small steps. Okay, there's no interesting choice to make here. Obviously, it's going to be induction on the first thing. So let's look at that. And this case looks pretty easy. By the way, at this point, I'm going to stop filling in all these tedious details whenever eauto proves it. So for this one, the star relation is reflexive by definition, so obviously this term steps to itself. And eauto doesn't just do this one, unfortunately. So what we have here is a big step telling us that, let's see, we know how to get from, so we're applying E1 to E2. We know how to get from E1 to a lambda. That's good, that's progress. We know how to get from E2 to a value, that's progress. And we know how to get from the result of the appropriate substitution to exactly the value we're looking for. So we're really close to done here. What could we be missing to finish this proof? E constructor, not the best idea for this particular term, I think. So basically, we want to compose together these three sequences of steps into one sequence, and that will give us the answer we're looking for. We can apply transitivity here. I proved this earlier. I didn't go through the proof, but I mentioned we had it. It's called star trans. And actually, let me be explicit and give the intermediate term that we apply transitivity with. We want to get from here to here. Where do we stop on the way? Let's stop at apps x e1 prime, which is precisely what we know e1 has a way to step to. So how do we prove this one? This is one of those lemma moments where we want to realize something bigger to prove with induction. We want a kind of congruence rule that lifts small steps to work inside of larger derivations. That is, that lifts repeated small steps to work inside larger derivations. So let me show you what I mean. I'm going to copy, actually, one of the rules for small steps when I find it up here. Actually, I'll copy both of these because we're going to want rules for both of these eventually. Let's prove a lemma called small app1 prime that looks just like its namesake, except I'm going to write star here and here. So this says if you can get from E1 to E1 prime in 0 or more steps, then you can also get from this one to this one in 0 or more steps by basically pushing this derivation down inside the left side of the application and leaving the right side alone. The original rule only told us we could do that for single steps. We're going to lift this to repeated steps now. And it turns out we can do this by, not many choices here either. Let's do induction on the first thing and see if T proves it. Yes. And we can apply the same surgery on this guy and say, oh, that doesn't change. We're going to have a star here and a star here. And now, do induction on the second one and get that. So let's remember these two facts. Star F1 prime, star F2 prime. Oops. Whoa, something weird happened. Not found, what did I call it actually? Oh, small, sorry. All right. So now, here's where we were before. We wanted to prove this fact where we had this step where we know how to get from E1 to this abstraction. We can accomplish this by using small app1 prime. And now we have our assumption exactly. And one sub-goal left. And here we can just use transitivity again. What do I want to use as the middle point of our execution for this application of transitivity? If V is our final goal and we're currently at this application, where do we know how to take a step to next? Yeah?
Subst V2 x E1 prime.
I think we're not, well, I guess we could do that. Yeah, why not? It's not quite following the linear order of things, but let's try this. Okay, so now we need to get from this application to this substitution. So we can't use beta directly because E2 is not a value, or it might not be. So we'll need to use another transitivity. And what's a good middle point for this one? Well, we already used that one, so we probably don't want to literally use it again. Maybe I just didn't hear you right. V2, okay, sorry. Yeah, that should work. This one looks pretty easy. This one's just reflexivity. So maybe we didn't even need to do that transitivity here. I guess we did. Oh, right, it says E and V, so we're not quite done yet. And now here's where we use that second lemma we proved above. And this one's by constructor. Every lambda is a value. E2 steps to something. Yep, we happen to know that. We know the beta rule tells us this one. Oops, something's not quite right. E constructor, because we want to know, oh, sorry, it's not that. It's we want to apply the rule for taking a single step, which was defined as star step. It still needs E functionality. And Now we can apply the beta rule. And it might look almost like we're stuck here, but we happen to have, by purest coincidence, proved a lemma for this earlier. Anyone remember the lemma? We know that any big step result is a value, and that's what we need here. So let's do big step value, and I'll just chain E assumption with that. Now we need to know this substitution steps to itself, and now we're ready for reflexivity. And here's one of our assumptions again. All right, so that was pretty tedious. We can make this go away by doing eauto using star trans. I haven't added star trans as a hint because transitivity tends to blow up proof search in horrible ways. So you want to opt into it very explicitly when you need it. And you also might need more steps than the default. 10 might be too many, might be too slow. Still not, 7's not enough. Is 8 enough? I forget if I got this to finish in a reasonable amount of time before. It's not. It might need another hint of some kind. Here, I'll just briefly remind myself. Apparently, oh, I ran T first. Maybe I need to do that here too. Let's see. I might also be missing an important step that I used in T over here. Let's just see what I had here. I'm not sure what the difference is. Take one more moment to see if I can figure out what's different about this. Oh, we forgot big step value as a hint. So I'll put that here. Because we did indeed use that, so it makes sense. Yeah. All right. Apply with is so when you use apply, sometimes you're using a rule that has some quantified variables, not all of which are implied by the form of the goal. With lets you fill in some of them that are not directly implied. For instance, for transitivity, you have two terms and you're trying to meet in the middle somewhere. You don't know exactly where you'll meet. You can say explicitly by using with. Okay, any questions about those proofs before I go to our third and final version of operational semantics? Okay. So the next notion of operational semantics uses something called evaluation context, which we saw a little bit yesterday in Amal's lecture. And it's kind of a nice abstraction to reduce the size of a semantics. It won't pay off too much for lambda calculus, which is such a small language, but for larger languages, it'll save a lot of effort in writing down the semantics. And it sort of factors out commonalities across rules. Like we saw two rules, one for the left side and one for the right side of an application. Evaluation context helps us factor out the commonalities between those cases. So the main thing we're going to do is define a type of evaluation context, which includes this box, which we call a hole. The idea is an evaluation context is an expression with one hole that we're going to fill something into. And so a context could be a hole, or it could be a context followed by an expression, or it could be a value followed by a context. And we have an operation, CE, that means plug E into the hole in C. And we can use that to define our small step relation with just one rule instead of three. And it looks like this. Take any arbitrary context. Well, I'll give myself a little more space here. I'll write it over here. Take any context and plug into it what we call a beta red x, or a term that's ready to have a function applied. And this will step to the same context where we're filling the hole with a different term. That's going to be that value for that variable substituted in that term. And the one side condition is that v really is a value. So this is easier to understand with an example. So let me step through evaluating this big term here with evaluation contexts. We have so this is the one that has 4 copies of the identity function applied in the right way. That takes us back to the identity function again in the end. So we want to evaluate this term. The first step is to find a place within the term where evaluation deserves to happen. This is callbyvalue, so that place is always the leftmost candidate that is not underneath a lambda. So in this case, it's this term. And we can formalize that with evaluation context by showing this is equal to some context C1 with some term E1 plugged in. And the context we use is going to be a hole applied to lambda xx, lambda xx, and E1 is going to be that same sort of term. So we've taken this term and factored it into a term with a hole in it, and then a value that fits inside the hole to get us back to the original term. So then we apply the beta reduction rule inside E1, and then this takes us to just lambda xx applied to what we had written over here before. And if we want to take another step of execution, now we realize this guy underlined here is the place to do execution. And that's equal to some context C2 applied to some term E2. And now that context that we want to pick is going to be lambda xx applied to a hole. And the thing we fill into the hole is exactly this red x that we're prepared to reduce. So now that's going to reduce. And we'll get down here to simply lambda xx applied to lambda xx. And now the whole thing is a red x. We can express it as equal to C3 applied to E3. And because the whole thing is a red x, the context is just a hole. And the expression that goes into it is exactly the whole term. And then this will step to the final answer. So that's how evaluation contexts work. They let us express this relatively complicated evaluation strategy using just a single execution rule. Any questions about how that derivation works? Okay, so we can formalize all this in calc. There might not be enough time to prove all the inclusion theorems, but let's at least get started and see how we formalize this. We can define an inductive data type of context, which follows exactly that grammar definition from over there. Right, and the second part of this is going to explain that. So the remark was that the app2 case here isn't enforcing that its first argument is a value. It's letting it be an arbitrary expression here. Where that gets forced to be a value is going to be in the definition of the plug relation, which stands for that operation of putting an expression inside the whole of a context. I'm defining it as a relation here because that's easier to do than with a function if I want that nice eauto proof automation I just showed to work. By doing it this way, eauto will magically choose the right context to make proofs work, which it's harder to do if you wrote a regular recursive function. Also, it's a convenient way to add side conditions. So here's the rule for plugging a value inside of an app2 context. We have some expression E1 and some subcontext C. We're plugging E2 in for the whole. We check first that E1 is a value, otherwise we're not allowed to plug. And then we recursively plug E2 into the context C to get E, and then we bring E back up and use it to replace the context in our original context pattern here. So this might take a little staring at to digest, but take my word for it, it captures the intuitive notion of plugging a value in for a whole. And then we have our one execution rule, which says you can take a step from E1 to E2 if E1 is the result of plugging this term into a context, E2 is the result of plugging this term into the same context, and these two are exactly the usual things you expect from a beta reduction. All right, and we can prove that small step and context step are exactly the same relation. It's sort of simpler to state these properties than in the last case. And then by transitivity, these are all, context step is also connected to big step, so all three of these are related in an appropriate way. They're equivalent at least for terminating programs. So we might like to show that small step implies context step. Let's try doing that. Let's do induction on the first thing, because there aren't many other choices, and we can optimistically apply the automation we built before. We have 3 cases left, so apparently none of them were completely eliminated. We'd like to know, actually there's one reason that might be true, which is that I neglected to add hints for the new judgments we defined, namely plug and context step. So we might get some of these now. Indeed, one of them was taken care of for us. But we have this one where we know how to do a context step from E1 to E1 prime, and we need to show how to do a context step where we've wrapped an extra application around it, so there's an extra E2 at the end. Any ideas what to do here? This one I think is relatively easy to handle. Inversion is often a safe bet to try it first. If you just keep doing it mindlessly, then you can get into funny infinite loops, but let's do inversion on the induction hypothesis here. So now we see that we found a beta redex somewhere. Plugging in that beta redex inside a context gives us E1, which is exactly what we see over here. And plugging in the substitution, the result of substituting gives us E1 prime, which is exactly what we see here. So we should be able to make this context step work by taking this context and wrapping an extra app1 around it. So let's see if eauto figured that out. Yes. I'm assuming that's what it found. And there's a good chance the same proof strategy will work here. So we can I'm going to go back and modify our tactics so it understands this too. Whenever we see a context step, I'm going to do that, exactly what I just said. There's only one rule for context step. So I'll make a copy of this to let us redefine it closer to our new definitions. Here is T prime that also looks for a context step to invert. Boom, boom. Yes. Okay, so I picked the easier direction to do first. I think there's more work lurking behind the other one. So let's see how that goes. So we want to show every context step has a matching small step. And you might remember context step has one rule, and there it is. It's not recursive, so let's just use destruct instead of induction. Let's do case analysis on how context step was proved. Although actually, right, we can do that. And also the T prime we defined will do that for us automatically via inversion. So we have this case where we've plugged like so into something, and we want to show we can get from E1 to E2. Where something like this happens. This one takes a little more thinking than some of the previous examples to generalize into an appropriate lemma to prove by induction. Does anyone have any ideas? Probably not worth pausing more than 20 seconds to see if there are some, and then I'll sort of spill the beans. Sorry? Version on H1 probably doesn't help too much because every one of the 3 rules for plug could actually work in this case. That could have been how we derived H1. And then we'd be in the same boat we already are in, because every one of those would have most of those would have further sub-hypotheses that we would be tempted to do inversion on, and we'd get in one of these infinite loops of inversion. That's a useful thing to have. I'm not sure we need it here. But how would we use it if we had it here? It's not ringing a bell for me, but maybe, I don't know, if you could flesh it out more, it might suggest something, but I'm not sure what to type. So at every place you're thinking generalized dependent, I'm thinking lemma, so maybe you want us to prove a lemma. Oh, sorry? Sorry? Okay. So yeah. What exactly is lurking here? We want to, I think actually the easiest way to do this is to take the definition of context step and prove a lemma where I've expanded that definition. So let me just copy that from over here. Something like that. No, sorry, we want something more general. So I'm going to show how we can use context to wrap something around any small step. I think that's what I want here. Let's do something like plug small step. If I happen to know, I can get from E1 to E2. And the result of plugging for context C E1 is E1 prime. And the result of plugging for context C E2 is E2 prime. Then I should be able to get by a small step from E1 prime to E2 prime. So let me just write what this rule is saying in a more functional notation. It's saying whenever I can get from E1 to E2, I can wrap a context around both sides, and I can still make the same step. This is very similar to what's written here. This version is sort of hard-coded to making this premise be about a beta reduction. But we need the more general fact that any small step can have a context wrapped around both sides. And then, let's see how this goes. And I'll be a little conservative and quantify the C and the E1 prime and the E2 prime as late as I can get away with. Now let's try, I think we want induction on the small step, and our tactics aren't quite ready for this one. I think they need a little more help. Is this what I expected to see? Maybe I actually want to do the induction in a different order. Yeah, probably, I do. So let's do plug C E1 prime. And then later have E2 and E2 prime, where we can small step from E2 to E2 prime. Okay, this is looking better. The reason this is a good thing to see is we have this place where we're plugging into a known context, so we should be able to simplify that. For instance, I can do inversion on H0, which should tell us that E2 prime equals E2, because plugging a value into a hole just gives you the original value. And now we have small step. Yeah, once I subst this, maybe this is clearer then. This doesn't quite make sense, so I've made some sort of subtle mistake here. I meant small step from E1 to E2. Okay. Try again. Now it's assumption. So the key thing we did here, we noticed we had a plug hypothesis where we knew the form of this first, of what the context is. So an inversion will tell us exactly how the plug operation turns out. So I can embody that wisdom in this tactic here and say, imagine you knew some plug fact. This next one's going to be a little twisty. Let's do inversion on it. and subst and clear it. And then this last part says fail if this generates more than one different subgoal. In other words, we only do this in cases where we can identify a single rule that was used to conclude this fact. In the other cases, we'll leave alone those hypotheses. This helps us avoid infinite loops. So now we might be in good luck here. Yeah. So that proves plug small step. And then let's see if this is enough as a hint to finish the job. Yes. All right, yeah, so that was the end. We now have all the, I haven't explicitly proved the other two inclusions between context step and big step, but effectively these four lemmas, these four theorems show the equivalence of the big step, the simple small step, and the small step with evaluation contexts. Any questions about anything we've just seen? Isn't that what evaluation contexts do for us here? Right. It's not obvious that you're not just talking about a relatively shallow encoding choice. Yeah, maybe we should talk separately about that. I'm not sure what the quick answer is. Yeah.
So do you have any recommendations between these three? Which ones you find easiest to use and talk?
So it really depends on what kind of theorem you're proving, and maybe that's a good segue into this one last example I put here at the end.
Abstract machines.
Yeah, I'm not going to talk about abstract machines, but so big step semantics tends to be useful for verifying compilers because a compiler optimizer might change the number of steps that a program takes to run. So it's good to use a semantics that hides the number of steps somehow. So this is a really silly program transformation that, well, it's not really silly. It performs all the beta reductions available in a term at once instead of just picking one, except it stops before going underneath a lambda. So it's a somewhat arbitrary program transformation that we might want to prove. I'll make more space here. We might want to prove preserves program behavior, and the most natural way to do it is to show that for any expression, if it evaluates to some value, then after we run this do some beta, it still evaluates to the same value. And this is pretty easy to do by induction on big steps with simplification. And we wind up with a term that might remind you of your optimizer from the hands-on session. If I do some further case analysis here, then this one quickly gets down to the heart of things, and simple and star was another important ingredient for that. Not sure I remember exactly the fastest way to finish this proof, but let's see if I can just pull that up quickly. I guess I did this more manually in the proof I have here. Yeah, there was some other inversion. Just take my word for it after I copy and paste this in. You can look at this later, but it's not too bad of a proof. I guess I didn't bother to make the completely automated version. There's some important inversions in there, but mostly eauto could do it. So that was a pretty straightforward proof. Doing this with small steps, I couldn't even figure out how to do it. Of course, there's a downside to formulating this with big step semantics the way I have here. Can anyone think of a reason that this is not actually the canonical correctness theorem for a program transformation? Right, this theorem tells us nothing about the behavior of the transformation on non-terminating programs. It could completely change the behavior. They could all start terminating somehow. Of course, the transformation, Turing tells us, can't just examine the program and say, if halt, then this, else this. So maybe not that big of an issue in practice, but indeed we know nothing about the behavior on programs that run forever. So that's a case where you might want to use small steps to phrase a proof like this, but it's generally more work to do that because the transformation can change the number of steps in the program, and you have to match up one step before with 2 steps after, or the other way around, and it's a little bit inconvenient to do. And then in my lecture tomorrow, I'll show a case where small step is clearly the right choice, which is soundness of type systems. And I'll actually use I'll use both the versions with and without evaluation context to show some of the differences between them. All right, well, I think I'm done. Any last questions? Okay, thanks.